Welcome back. So, we're going to do a deeper dive on the homework for Chapter 2. Once again, I'm going to show you some of the trickier problems so that you understand the basics of how to go about solving them. You can try them on your own, but I'm giving you some guidance. Not all of them, but a good portion of them. Okay, open it up. Homework 2. I'm going to start with number 1. It's not a hard one, but it's kind of confusing at first. We talked about Robert Millikan and the oil drop experiment. What we maybe failed to mention is that some of the oil droplets had multiple electrons. And so by figuring out the ratio that all of them had, you can figure out, okay, what must be the charge of one oil droplet? And so you found one oil droplet is 1.6 times 10 to the negative 19th. So we can't go smaller than that. But there is the possibility of being multiples of that. So 1.6. I don't see any value. 1.2, no, that's too small. Well, we don't see any 1.6, but we do see 3.2. 3.2 is a multiple of 1.6. It's 1.6 times 2. Next multiple we see is 4.8. We've added another, it's a multiple of 3. From 4.8, the next one would be 6.4. So we're going to bypass this guy. I don't see a 6.4. The next multiple would be 8. And the next multiple would be 9.6. So we're looking for multiples of 1.6, saying, okay, these are possible charges that oil droplets had. They had 2 electrons, 3 electrons, 5 electrons. So I just wanted, that's how we go about solving that one. Jumping ahead. Just one example or 2 examples of this. So we need to utilize our periodic table. So the protons of americium 240. So americium on the periodic table, I'm going to look at my periodic table over here. Americium is AM 95. Now please note, on my periodic table, it says americium 243. So if I used my periodic table and only my periodic table, I would get the neutrons wrong. Always use the neutron count for the element given. So it's neutral, so the protons and electrons must be the same. So the proton-neutron count must add up to 240. So 5 short of 100, and then 140 beyond that. So it should be 145. So 145 plus 95 is 240. Now, the most common form of americium would be 148, but I must always use the one offered to me. And do number 6. So, okay, how many protons are an ion with 18 electrons and a -1 charge? -1 charge means we have one more electron than we have protons. So the electron count is the only thing that can change. So one more electron, so that means we must have 17 protons. How many total number of electrons in a strontium 2+ ion? Strontium neutral, looking at my periodic table, is 38. So in a neutral compound, it's 38. 2+, I've lost 2 electrons, it must be 36. I'm going to jump ahead to 8. Basically the same idea. We're going to turn the protons, neutrons, electrons Or use the protons to find the elemental symbol and then find the number of electrons. Or make sure you scroll down and answer all the questions. But 8 and 9 are isotopic abundances, and so I want to show those. So chlorine is 34.97 with an abundance of 75.77 and 36.97 with an isotopic abundance of 24.23. Now, yeah, you can look up the answer, but that's not the point. The point is, how do we get those numbers from a periodic table? The periodic table is, so if we have a 75% chance of getting essentially chlorine 35 and a 25% chance of getting chlorine 37, the atomic mass is going to be closer to 35. So I'm going to multiply those together and divide by 100 because these are percents. So 34.97 times 75.77 divided by 100 gives me 26 point, what's a 4, keep 4 places, 4, well, I'll keep it 497. I'm going to keep 1 place past the proper, so I'm only really supposed to keep there, just so my rounding doesn't get off. 30, the next guy, 36.97 times 24.23 divided by 100 gives me 8.95, we'll say 8. And then we're going to add those together. So 26.497 plus 8.958 gives me 35.455, which gives me 35.46. I might be off by a smidgen. 35.45 is what I would get if I looked up on the periodic table. A harder one, titanium. Harder one, titanium. We have 3 isotopes. 45.95263 with an abundance of 0.78300, 78%. Then isotope 47.94795 with an isotopic abundance of 0.13500. Then finally 49.94479 with an isotopic abundance of 0.08200, 8%. If you're converting them to percents, don't forget that 8% is going to be 0.08 if I've divided by 100. Now it's 78% titanium 46. So my math, when I work this out, should be pretty close to 46. 5263.78300. Keeping all these to like 5 decimal places based on 1, 2, 5 sig figs. Just about 35.981. 7.94795, 13500. This one's giving me 6.4730 rounds, and 49.94479, my 8%. 8.2%, 4.0954. So adding all these guys up, 35.981, 6.473 plus 4.0954 54. Out of that, I get 46.54. We're going to 9. It technically had a 4 after it, but I'm writing it to 5 places. What did I say? It's pretty darn close to 46. Between 46 and 47. It's only a little bit closer to 47 because we have 46, 48, and 50. So it's closer to 46 than it is to 50. Okay. That's number 9. Jumping straight to 13, where we actually have some mole math. Okay, so there's 6.7 moles of iron chloride. So moles to atoms or moles to formula units uses Avogadro's number. For every 1 mole, there is 6.022 times 10 to the 23rd of something. This is a mole. They're our mole day. So we are just multiplying those across. It's pretty straightforward. We're going to get a big number. 6.7 times 6.022. 10 23rd. You get 403 times 10 to the 24th. 403 times 10 to the 24th. That should be very easy. So make sure when we type it in, though, we do say 403, and they have a little tool. Oh, put that in there, and you can just type in then 24. Make it easy. Looking at 14. 14 is a little bit more tricky. So let's line ahead. There's 81.0 moles of P4O10. How many moles of P are there? I'm not even going to bust out the dot cam because it's like, okay, just note that P4O10 means there's 4 P's for every 1 mole of P4O10. So what's 81 times 4? 81 times 4 is 324. I'm not even going to set that up. 324. But you got to just look at the elemental formula. So last one that I'm going to do, last one on the assignment. How many molecules are in 2.37 moles of SiF4? How many moles are in 5.13 times 10 to the 24th molecules of SO2? So we're just doing moles to molecules, molecules to moles. The trick here is just make sure you got your order of operations right. So moles to molecules. So you're going to multiply by, for every 1 mole, there is 6022 E23. For molecules to moles, there's 6022 E23. You gotta make sure you get the order of operations right, or you're going to get way wrong numbers. When I go moles, there should be a lot of molecules. I'm not even multiplying this. But so my molecules is 1.4. We're going to say 2 times 10 to the 24th. And when we go from molecules to moles, we should have very small amount of moles, relatively speaking. This is where we got to be careful. Times 10. If you just try to type it in like you see it, divided by 6022 times 10 to the 23rd, you're gonna get, I got a really big number. And so I did it wrong. Critical thinking should tell you I got it wrong. So how can I fix that? easiest way to fix that is by using the double E button. 5.13 double E 24 divided by 6022 double E 23. And so my number of moles is 8.52. 8.52. So the trick here is to make sure you know how to set this up so you're not going to get burned by order of operations. And you know what looks right based on logic and critical thinking. That tells you when I go into moles for molecules, I'm going down. When I'm going moles to molecules, I'm going up. Number, and when I'm going molecules to moles, I'm going down. So that is what I wanted to show you from this assignment. Have a good day.